Another related calculation, which is presented in Chapter 5, but I think relates better to the concepts we're talking about now, is what do you do when the reaction's done to test not only how successful it was from a perspective of how much product did you make, but also did you make the right product? So this is really important as well. If you doing a chemical reaction to create some new product, some new drug, molecule, or some new chemical product, it's not only important to get the right, to get a high percent yield, but it's also important that you're able to measure something about the purity of the product that you've made. And so calculating the percent mass of an element in a compound is one way to do that. So what scientists sometimes do, a lot of compounds involve carbon, as you saw. The aspirin, for example, involves carbon. Right, so the aspirin has a specific formula with 9 carbons, 8 hydrogens, and 4 oxygens. And if you let's say you've made some aspirin, right? You put in a certain amount of reactants, you got the aspirin, you measured it out, you got a decent percent yield, but you really still need to know, is that aspirin pure, right? You can't sell it if it might have some impurities in it, something that could be dangerous. So to determine if it's pure, one way to do that is to measure the percent mass composition of the carbon and hydrogen and see if that matches the percent mass you should get based on the formula for the substance. Right, so if I have pure aspirin, all my molecules have C9H8O4, that means there's a certain percent of the mass of that substance that comes from carbon. A certain percent of the mass of that comes from hydrogen. And since the formula for that is different from the formula for other things, each thing will have its own slightly different percent mass for the elements that are involved. Right, so one way to do that, if you have a carbon-containing substance, if you've got a lot of carbon, the percent carbon can be measured by burning the substance. You burn the substance, you figure out how much ash is left over. That tells you how much carbon there was because you're burning off some of the other elements. If you can break that substance down and through some reaction, could be burning or some other reaction, to figure out if you have a gram of this substance, how much of that gram was actually from the carbon versus how much was from the hydrogen versus how much was from the oxygen. You can match that up with this formula, which would give you your calculated percent mass. So you can measure it, compare it to the calculated to see if it's the right substance. So if you had aspirin, which is C9H8O4, how would we figure out what the percent of that is actually carbon? Well, we would use the formula. So if we're looking for the percent carbon in C9H8O4, it's going to be the amount of carbon over the total amount. So how much carbon do I have? I've got 9 carbon atoms, each with a mass of 12.01 AMU, or grams per mole. So let me I'll put the units in here so it'll be more complete. So I could think of that as 9 moles of carbon, each with a mass of 12.01 grams per mole. Put this. 9 moles of carbon, 12.01 grams of carbon per mole of carbon. And then I'm going to divide that by the total mass. So there are 9 moles of carbon in every 1 mole of the compound. And the compound is everything. So that's 9 carbons plus 8 hydrogens plus 4 oxygens. So that's 180.154 grams of the compound per mole of the compound. So this cancels. So then I multiply that by 100, and I would get 9 times 12.01 divided by 180.154 times 100 gives me 59.999. So to 4 sig figs, 59 will actually be 60.00% carbon. And so the idea here is I make the aspirin, I do a reaction and break it down and figure out how much of the aspirin is actually carbon, measure that experimentally, and if I can show that exactly 60% is carbon, then I have an idea that the aspirin is probably pure. Because if the aspirin were contaminated with something that had a different formula, that other formula would give me a different percent carbon. And that would skew the percent that I'm measuring from 60 to some other number, depending on the other formula of the substance, the impurity that's in there. So calculating the percent mass is a good way to get an idea of the purity of something. We could also get the hydrogen out of this. Measure that experimentally and calculate the percent hydrogen. So we'd have more certainty if we did the percent mass for more than one element. So if I wanted to calculate the percent mass for hydrogen, it would be the same formula, but the top part of the fraction would be different. Instead of working with carbon, I'd be working with hydrogen. So I would say that I've got 8 moles of hydrogen, and each hydrogen is 1.008 grams per mole. So that would cancel. So the hydrogen in this sample is only 4.476%. Right, so every formula, if I use every formula, a different formula, I would get a different percentage. So if my experimentally measured percent hydrogen matches the calculated percent hydrogen, then I have a good confidence that the substance I've collected is pure and that every unit of it in that sample has the same formula. Questions about that? So here's another example set up the same way. You can work in grams per moles or you can work in AMUs per atom. Just you get the same answer, right? Because whether you're looking at the AMUs of an atom or the grams per mole of an atom, it's the same number on the periodic table. You'll get the same percentage. So there's lots of examples. We could do it for lithium. So lithium carbonate is one of the lithium-containing compounds that's used as a mood-stabilizing drug. If people take lithium, then this may be the drug they're taking. The carbonate is really mostly inert. It's just a way of introducing lithium ions into the system. So if we want to know that a patient's getting a certain amount of lithium, we would need to know, if we're giving them the lithium carbonate, how much of that is actually lithium, so that they're getting the right amount. So we would want to know, if you have a gram of this lithium carbonate, how many grams of lithium are you actually getting? So the percent composition gives us that relationship. Once we calculate it, we can use it as a relationship for further calculations if we wanted to. But if we want to know the percent lithium in this compound, we would get the mass of the lithium, which is 2 lithium moles, or 2 atoms. I could do atoms and AMUs instead of grams and moles if I want. 2 atoms of lithium per molecule. And I've got lithium's AMU is 6.941. So I'll multiply that by 6.941 AMU per atom. So that cancels. I'm going to divide that by the total mass of one unit. So I've got 2 lithium plus 1 carbon plus 3 oxygen, and that's 73.89 AMU for the whole substance. So this is AMUs of lithium, this is AMUs of the compound. So I multiply that by 100 to get it as a percent. So it's 18.79%. So if I give someone a gram of lithium carbonate, how much lithium are they actually getting? 0.1879 grams, right? Because 19% of it is actually lithium. The rest of it is just carbon and oxygen. Right? So that's a relationship. Now, as a percent, that means this is a relationship. 18.79 grams of lithium in every 100, so it's a percent or per century per 100 grams of the compound. So that's another nice thing about calculating this percent composition is I can use it as a relationship. So I already have the mole relationship. If I want that, that's already here, right? 2 moles of lithium for every 1 mole of the compound. That's given in the formula. But that doesn't tell me the mass relationship. So if I want that, I need to do the percent mass. So the percent mass is useful for determining purity because I can match it up with something that's experimentally measured. It's also useful, it gives me a relationship, so I know if I'm supposed to get a certain dosage of a chemical or a dosage of a substance, I know how much I'm getting because I have the relationship relating to how much of that substance I actually have.